We will see more in 4D integral calculus. So the problem with integral calculus when we grow, the problem in integral calculus when we grow in dimension is its kind of spatial interpolation. So that is the biggest thing. Like if I have 1D, if I have 1D, then I can imagine it. If I have 2D, then I can imagine it. Or if I have, okay, so this is vertical, this and this. So if I have 3D, then I can imagine. So spatial way, it is imaginable. We can imagine it. But beyond this, it is non-imaginable. So whatever we are talking now, that is 4D and beyond, so we are entering into machine learning and artificial intelligence, where we have the kind of the dimension. So if you see the machine learning, then you have set of samples. So set of samples are nothing but it can be considered as the instantiation of a class, where the number of features what we see, those are the dimension. So those are the attributes of the class. And then whatever the class we see, so that is the class. Okay, it belongs to class A, class B, class C, class D. In machine learning means those are the classes, class A, class B, class C, class D. So whatever the sample that belongs to a class A, those are instantiation of class A. Against each feature whatever the value we are seeing, those are the attribute value. Now each feature can be considered as dimension. So there the problem starts. So there we hit a dimension reduction. Okay. So dimension reducibility. So in that way we go for orthogonal components and we reduce the dimension so that their ein vector and those things comes into the picture. Now consider that all the features are orthogonal based upon ein vector. Now, the problem starts with the number of components, that number of features that is post resolution in kind of dimension reductionability. So if I see, then it is beyond 3. Then how we can imagine it spatially? So difficult. Let's try a 4 component, and then probably it should be kind of more clear. Now the 4 component integration when we see, let us start with one component. If I have one line, then that is independent component. So it is x, then fx we consider, now we don't consider as in orthogonal component. Fx is nothing but density function. If it is a density function, then at any, if this is the line, then at any point x, if I try to see, then I have fx. So density at point x, I know. Okay, so if I know the density of point x, then what is the kind of uh, density into length, for the length delta x around the x. So if it is x here, then delta x around x multiplied by the density at fx, it gives us the at weight of the line with the length delta x. So, or if I see in kind of other dimension, if it is fx and it is fx, then at x, okay, if I have delta x around it, then it gives the area of the rectangle. So that is the concept. If rectangle delta x is very small, then whatever fx we are thinking of, so fx need to be estimated within delta x. There can be many value of the fx in the delta x. If fx is very small, then I can take one delta x, any one value, that is fx. Like that here also, if I go for density function, then delta x, if it is small, then any point within delta x, one point I can take as fx, that is the density function. So that fx, if I multiply with the delta x, then I get the weight there. So what is difference between integration and typical addition? So integration provides addition through area or through density function. Now this is another branch we can say, but it is a function in independent component. So that is the difference. So function in independent component. So if fx is x to the x square, fx is x square or 1 plus x square. So when there is a line and there is a origin, then at the origin the density is 1, but as we go, the density increases x square. So at the end it will be very heavy. Now if I try to find the total mass of the rod of the bar, then if I take any x and with at x with distance of delta x, if that slab, if I calculate the weight, then it will come as fx dx integration. So 1 plus x square would come as x plus x to the power 3 by 3. Okay, so the greatness of calculus is whatever we are getting, that is in function of x. Now if x is 1, I can place it, and what is the weight of the first unit length? 2, 3, 4. If x is 10, then this way. So nice, right? Means I can say algebraic addition or addition through algebra is integration or calculus. Differentiation, same thing. If I differentiate, that is also called, so integration is also called antiderivative. But we can say differentiation as anti-integral because integration comes first, then differentiation. So differentiation is anti-integral. Now differentiation also, if I have formula, if I have algebraic formula, then differentiation also comes as kind of in a function of x1. That is the greatness. So whatever we receive, like if I have equation of a graph that is function of x, then what you want, that the addition what we are expecting through integration or area or volume, next we see, and beyond volume. So that is fourth dimension. So everything we get in function of x only. Now just substitute x to some value and keep getting the volume, area, or bigger than it. So nice. So that is calculus. Okay. At the end, calculus means you are amazing. It is like a calculus and a vector. If you are thorough, then you can do invention in machine learning artificial. There are nothing but calculus and vector one. That's it. So anyway, now there are tons of video, 9 or 10 episodes we have uploaded in the orthogonal component. So if you get orthogonal components in machine learning somehow, then you can do computation only based on orthogonal component. No need to go for full-fledged computation. Like if I have a building and it is made of brick wall, then each brick I have to think. If I take away 4 brick, then wall becomes weaker. In that way, your house becomes weaker. So if it is made up of 5,000 brick, one room is made up of 5,000 brick, then each brick is important. So that is the normal programming. But that room, if I make with a 4 pillar, then brick is no more important. You can take away all the walls, but your room will be exactly like this. You can keep changing the wall you want. So this is comes under design. Okay, only matters is 4 pillars. There you cannot take out anything. Otherwise, full house you can keep changing it. Like that way, if you understand orthogonal components, then even though the database is very big, but database all database full can be you can say it can be represented through the few orthogonal components, and you do manipulation through orthogonal component, your work will be done. No need to go for thousands of data, uh, thousands of kind of separate data to do the computation. If you are able to find 3, 4 orthogonal components, then you are done. Here, rather than going orthogonal component the way it is going x, y, z, then we enter into density function. So density function is the fourth orthogonal component. Now we visualize the density function in single dimension. In double dimension means if I have independent component in xy plane, this is x and this is y, this is x and this is y. So this is surface. If this is surface, then surface at each point I have xy. So on the surface, each point I have xy. So function over xy is fxy. That is the vertical component. Okay, that is spatial. So everything we are making a spatial. Spatial means SPAT, spatial. That is spatial. Okay, so everything we are making spatial. So fxy is vertical component, and we can imagine that fxy together with the xy plane, it's make a 3D. Okay, this is one concept. Other concept is that xy plane leave it is as xy plane only, and fxy consider it as density. So if this is origin, this is x-axis. If this is origin, then this is y-axis. Now, from the origin, if I move in x and y direction, everywhere the density, if it is a plate, then everywhere density is different. That is also equivalent to vertical. This is density function. If it is equivalent to vertical, then in 2D only I have 3D. Now, at any point x comma y, if I take an area with delta x and delta y, then I have area as delta x into delta y. If I multiply that area with the density function at xy, where delta x and delta y is very small, if delta x and delta x and delta y is very small, then in small area, the density function will have very few points. If it is very big, then I have thousands of densities. Each point density are different. Then I have thousands of points in this area. So if I want to calculate the mass, then area into density. Which density I'll take? If I have area one is delta x and one is delta y, and delta x is 10 meter and y is 20 meter. In that region, which xy I would pick so that fxy into delta x delta y would be the net weight. Not possible, right? Means how thousands of value one I'll take, and then so I'll divide into small rectangles. So at any x comma y, the rectangle around it is delta x delta y. If it is very small, infinitesimally small, then the fxy, the xy point I need to take in that delta x delta y region are very small, probably 4 or 5 points. All the four corner at the center, or only 4 points. I can average it, and this way we go to then one rectangle. If I calculate the mass, then means delta x, delta y, and fxy. If I multiply in that rectangle, I calculate the mass. Or if I go orthogonally z value, then I calculated the volume, and then I can add all the rectangles. For one rectangle, I calculated. Again, calculus integration, you are so great, you are so genius that volume also, or the net mass in the 2D, in the 2D where xy are the independent component, you give in algebraic equation. So this is the greatness of calculus. My graph equation is algebraic, then integral equation is also algebraic. Now, once I receive, so for a particular rectangle, if I calculate fx at xy and delta x, delta y, whatever. Now, leave the geniusity. So each rectangle I get the mass or volume. Now, for all rectangle, if I add that fashion, then I get the complete mass. Okay, so this calculation may not be fit in the mass calculation as far as density is concerned, because whatever infinitesimal small you take, but still it will be inaccurate. Approximation will be, if you take small rectangles, then it will approximate to the best result, but it cannot be uh, kind of ideal. So these calculation that you take separate rectangle and then calculate the net mass, it is very useful when the density you have in a kind of okay, so uh, like cross section way. Uh, you say that when you calculate kind of like you have uh, a mountain, okay, where the cross section height you take. So cross section height if you take, so in that case it is a kind of I'm not getting the word. So like if you have a kind of a mountain and in z value, then you take kind of cross section, you take separate cross section in the zx. So contour. So contour is the word. So if you have the cross contours, I think it is understandable. So if there is a mountain and mountain I have cross section in z axis, then if I take the top view, against each x y we get separate contours. Like if I have, so only contours are available, okay, not the equation. So if I have algebraic equation available, then I'll go for pure integration. Otherwise, if contours are available in density also, if contours are available, then in each we'll divide the xy surface into separate rectangles, and then as per the contour for each rectangle I'll have fxy, that will be average one, and then fxy delta x delta y would be the net weight there or net volume there if contours are represent the height. Otherwise, if I don't have contour and fxy is completely in algebraic equation, then rather we'll go for pure volume calculation. So either I go for approximation, okay, it is sometimes called Riemann sum also. So Riemann sum is approximation where we divide the xy surface into so many rectangles, and each rectangle will have very few fxy. So very few xy, so very few fxy. So those few fxy I can have average or whatever any value I can take, and over delta x and delta y, that is the rectangle into fxy, there I calculate the mass or volume, then I add for all the rectangles. So this is mainly applicable when I have contours. Contours in the sense fxy is available as discrete values. If that is the case, not in algebraic value, if that is, that means it is digital. Sometimes digital are inferior to analog. So this is what we are saying. But if things are available in a kind of equation, then nice if we go for other part, that is the integral. Now let's go to 3D. So in 3D, so in 2D we saw area into height is the volume, or area into the density is the mass. In 3D, so this is if I take the kind of take the fxy as the height, then this is 3D. Two independent component and dependent component in height, then it is 3D. 4D. 4D, I have three independent components. There are two independent components, x and y, and z is dependent, fxy is dependent. Fxyz can be either vertical, then it is a volume calculation, or it can be density function. Now, in 4D, it has to be density function. We have to understand things as a density function only, because there is no four dimension that we can draw. So now I have three independent components, x, y, and z. So there are three independent components, x-axis, y-axis, and z-axis. So there is nothing called fxy. There is fxyz. So three independent, based upon the three independent components, f bracket x comma y comma z. If there are three independent components, then it should be considered as 4D, because the dependent component is the fourth one. Now, fourth one I cannot draw. So let's see, think that if I have a kind of, okay, so how I can kind of show it. Okay, so I believe it should be visible. Okay, this is a kind of big papaya. Papaya. Okay, so I was trying to open it, but I cannot open it. This is how I got it. Okay, so this is a big papaya. So the papaya everywhere the density is different. Okay, so that is the scenario. So the papaya, if I see, then density is different at different point in the papaya. So I can consider it as f x y z at each x y z. So if it is a 3D x y and z, if there is x y and z, if it is a 3D, then at each point now is x y z. At each point density is different rather than going for fourth dimension. Each point density is different. That is fxyz, fxyz. Then now that fxyz, whatever we are getting, 1 plus x into y into z, this can be a value. This can be an equation. Each point, the density is different. If density is different at each point, then if I take xyz, at point xyz, if I take delta x, delta y, and delta z, a volume string, you remember that if it was a bar, then at x I took delta x. If it was a surface, then at xy I took delta x and delta y area. Now if it is a volume, at xyz I took a volume string, that is delta x, delta y, and delta z. If I multiply that volume, that will consider as delta V, V for victory. Okay, so V for Vatican City. So if I have delta V, delta X, delta Y, and delta Z, if I have delta V, okay, then if I multiply delta V or delta X, delta Y, delta Z with fxy, then we get kind of another thing that is called mass. So volume into density is mass. Area into height is volume. Line into height is area. So from 2D surface, if I see, then we calculated the area. Okay, 2D surface into height, that was 3D, we calculated the volume. Now I have volume, and then each point in the volume has separate density. That is the future. So if we go in this direction, probably someone can think about more dimension than 4D also. So we can move along the machine learning or artificial intelligence where the number of orthogonal features are more. Here, all four are orthogonal. X, Y, Z are orthogonal because we can see it. X, Y, and Z. But density is orthogonal. In a way, the density has no relationship with X, Y, Z. Like the way Z has no relationship with X and Y. X has no relationship with Y, Z. Now I can say X has no relationship with Y, Z, and density. Z has Z has no relationship with X, Y, and density. So density is coming as orthogonal component, and that is the fourth one. So at each x comma y comma z, what is the density? So at each x comma y comma z, if I have delta x, delta y, and delta s, a small volume, in that volume, if I multiply with the fxyz, that is the density, then a small volume, we can calculate the mass. This is the Newton. Now that mass, if I integrate over x, over y, and over z, then I get the complete mass. So you remember that when we were calculating the 3D, we had xy plane and z was vertical and z is dependent component on xy. Then first we calculated xz plane. Whatever we got xz plane, that was in a function of y. So at each y, so y is in this direction, x is in this direction, xz plane we calculated in a function of y. So at each y, we have a value that is a function of y. If that value, if I consider in y direction, then it becomes a surface again. Again, if I calculate the integration, we get the volume. Okay, but in 3D, 4D, where we have x, y, z as independent component, then we are calculating if I do fxyz dx dy dz, fxyz dx dy dz triple integration. If I do, and if I do the dx calculation first, then I am first calculating area in xd plane. X is x axis and d is the density. Xd is a separate plane. In xd plane, we are calculating the area. Whatever comes, then we calculate the another area in yd plane. Whatever comes, then we calculate another area. If this is z axis, then zd plane. Whatever comes, that is the net mass, not net volume, net mass. So this is 4D. Okay, you can consider 5th D, 6th D, 7D. But someone thought about this. So I have not thought about it. So density function is not my invention. But still, we saw that how it can be explained and how it can be kind of generalized in 1D, 2D, 3D, 4D. So this is what we have done, and that is not available anywhere. That it can be density function generally people use in 4D, but we can go ahead and use in 3D, 2D also density function. So density function is nothing but fourth orthogonal component where xd, x-axis and density function is one plane, yd, y-axis and density function is another plane, zd is another plane. So if I do f y z dx dy dz triple integration, if I do dz first, then it is zd, z and d, then that whatever the kind of the surface what we are imagining now, in that surface we are calculating the area. Whatever comes, and if dz, dy and dx we have taken, then yz axis we calculate, and then xz plane, yz plane and xz plane finally we calculate. As far as integration is contained, if it is fx, yz, dz, dy, dx, then first integration, that is the innermost integration, would be function of x and y. Then next would be function of x, and x, that is the outermost, it should be constant. Let's consider now, like I promised that there should be example. So let's consider that fxyz equal to 1 plus x into y into z. Okay. Now if I integrate with dz, then it will come as xy z square by 2 because xy are constant. Okay. Now z square by 2, z I have to put through limit. Limit will be as a function of x and y. Okay, it can be x only, it can be y only, but it should be both also. So xy into z square will come in terms of x and y. So now we have to integrate with dy. Dy, the limit should be in function of x. So whatever x into y, x, x into y, and the limit is coming, first limit came as a function of xy. So x 1 plus xyz. So 1 became z. So z plus xy, z square by 2. So z square was replaced with some function in xy. Now it is difficult. X plus xy, again x and y function. Now I have to integrate with the y. So integration is becoming difficult step by step. Now the x, y has limit in x. So everything, whatever integration we take, it converted to full function of x, and that is very big. And then we calculate the final integration, and 0 to and any constant I have to put in the outermost limit. It won't be in function of everything. This way we calculate, we settle down the 4D, 4 dimensional, where the fourth dimension is the dependent component is the density function. Okay, so I'm thankful to the person who thought about. So density is not the actual density only. Density is kind of generic. Like I gave example. Okay, I gave example that I have a semicircle. If this is a semicircle and it is a, if this is a semicircle, oops, okay, if this is a semicircle, then this is x-axis and this is y-axis. Okay, so this is y-axis and this is x-axis. So this is the center. Now, if I this semicircle, if I make it like this, then it is xy plane. If it is xy plane, then can we now the z value, the fxy, if I consider it as z value, then fxy at x axis it is 0 and z value grows like this. Slowly it grows like this, the way y is increasing. So at here when y is 3, z has value 3. Fxy equal to y. So the 3D, okay, this example you may get many places that semicircle is there and it is a city and base is a ocean. Then what is the average distance of the city to the ocean? But this is explanation you want here that we are now thinking the y as the third dependent component. So now we have, so can we calculate the volume? So this is that xy plane and volume rises like this, okay, as y grows. So at any x-axis, the height is same because y is same. At any x-axis parallel to x-axis, height is same. Say height goes like this, or height goes from here, height goes like this. Okay. Now, can we consider fxy is y here? So, can we consider fxy as density function? Okay. If fxy is the density function, then if I need to calculate the volume, okay, then now I have kind of three things. Now I have, so if fxy I consider as dependent component, fxy, if I consider as dependent component that is z axis, then it is a 3D. If I consider the fxy, okay, fxy or fxyz, whatever, as a density function, okay, then if I need to calculate the kind of volume, okay, so I have a kind of option as considering fxy as the third independent component, or I can consider it as the fourth component. Let's consider it is a fourth component and I have kind of I have to calculate the volume. So if someone need to calculate the volume, then as we have described, density function can be considered as constant 1. If it is constant 1, then dx, dy, dz, we are calculating the volume. So here, the dz, if I integrate dz, then it will come as 0 to y. So it will become y dx dy. Okay, please concentrate here. So if I have fxy, fxyz, fxyz, dxy, dx, dy, dz, through this, we calculate the fourth component, that is the density. So if fx, y, z, dx, dy, dz, we are calculating the net mass. But if fx, y, z is 1, then we are calculating as a volume. So dx, dy, dz. If I calculate, dz has to be calculated prior to dy because dz is dependent upon y. So dz, if I integrate, the limit will be 0 to y. This is how it varies. So if I do the integration of dz, then it will come as y. So if I substitute 0 to z, so if you substitute 0 to y, then it is y. So y dx dy, same story we are repeating. So the calculation of density function, it also becomes volume, okay, rather than becoming mass if I take it as constant rather than equation. Okay, so someone can calculate through the density function also, where I calculate dz first, dy first, dz first, dx next, and dy at the end, or dz first, dy next, dx at the end, or dx first, then dy, dx first, then dz, and dy at the end. But dy will be always outer side to the dz because the z depends upon the y as per the equation. Okay, so I believe that integral calculus is coming to end. Little bit we'll talk about the polar coordinate and then kind of cylindrical coordinate and then the spherical coordinate. So polar coordinate makes sense when things are in angular fashion. Like anyway, we have angular way of calculating the things. Okay, so if I have a circle, okay, so if I have a circle, this is a circle. Okay, if I have a circle, then circle, what is the area of the circle? If this is a center, if this is a circle and this is a center, if I cut like this and angle is theta, okay, from center there is one radius here, from center there is another radius here. If I cut this, okay, I think it's called pie chart, pi. If I cut a pie and angle is theta, then what is the area of the cut? Now it is easy to talk in the polar code. What is polar code? So if I have x-axis, so and there is a radius like this, then x is r cos theta. If theta angle is there, then that is r cos theta, whereas y is r sin theta. So if I have r, so if this is a circle, if this is a circle and there is r, okay, and I need to calculate this area, then from center I take small distance r. So suppose the radius is so rather than r, so radius is, this is center and this is end, it is full radius. So if I take a small in between a circle, okay, there is another circle, that is imaginary circle, and that is the distance is r and angle is theta. Okay, if I want to find the, if this is r2 and there is another circle, so there are three circles now. From here to here r1, from here to here r2, and this is the net radius, I can say a. So from r1 to r2, if I take a strip and then theta angle, so r1, r1 and r2 and theta angle, this side also r1 and r2, I get a slab like this. Okay, if r1 is 0, then I get a pi, but if r2 is there, then I get a slab. r1, r1, r2, 0 to here r1, 0 to here r2, 0 to end is the net radius. So r1 to r2 at angle theta, then again r1 to r2. This strip I take, then what would be the area? So better to calculate this in a polar coordinate. So now doing in xy, rather doing in xy, I can replace x with r, where r cos theta is x and r sin theta is y. X square plus y square equal to r square. Means we know equation of this. So these are the relationships. If I know, then if my function is in, if there is fxy, then I can convert it to fr theta. Now there are two variations. One is radius. The radius would vary from center to end. From here it would vary. Like if I have a bar, then if I take any x, then x would vary from 0 to the end. If I center and there is a radius would vary from center to the end, and then angle would vary. So if I take the polar coordinate, then this is variation in the x in r and theta. So I can say fr theta, function over r and theta. Okay, if that is the case, then fxy would be converted to fr theta. Fxy dx dy, fxy dx dy. Okay, if through this way, if we are calculating the volume, then it will be changed to fr theta dr d theta. Okay, but it cannot be dr d theta straightforward, because if I have, if it is center and this is r1, this is r2, if this is if this is if this is center, if this is center, this is r and this is r1 and r2, then we are taking delta r distance. Okay, and here we are taking delta theta as the angle. So what is the, so if I calculate the area, okay, then this, if it is very small, then it will be calculation of this arc and this height. What is this arc? If it is delta theta, then this arc is r. So the r1, we're talking about r1 and r2. Let's it is r and delta r. Makes sense, right? Means r2 minus r1 is delta r. So from center we have r and then delta r. So r plus delta r is r2 and r is r1. Now I change to r and delta r. And theta is delta theta. Then, okay, so what is the length of the delta theta? So this is r delta theta is the length. What is the length of delta theta when it is full? Okay, then r delta theta, where delta theta is 360 degrees, that is 2 pi r. So this is how radian calculation started happening. So if I calculate the circumference of a circle, then it is 2 pi r. If I consider 2 pi as angle, then whatever the angle we have now with the radius, if I multiply, I get the circumference. 2 pi into r. So 2 pi is the angle that is in radian. So if I have delta theta and this is r and delta theta, then this arc length is r delta theta. If delta theta is 360 degrees, then it is 2 pi r. R whatever in radian is the delta. So this arc length is r d theta and this is dr. If this is center and this is the circle, from center I take any r and then delta r. Okay, and that I draw an arc, then also here is r and delta. If I want the strip area, then arc length and then delta r. So arc length is r d theta into delta r. So now if this is a plane on which we are talking about the story, then f delta theta, f r theta, the function over r and theta is the vertical one. So if I want to calculate the volume, then it will come as f r theta into dA, height into dA. A is area. Area is r d theta dr. So f r theta r d theta dr. F function over r and theta bracket close r dr d theta. R dr d theta is the area into function over r and theta. Then it comes as the volume. So wedge kind of, like I have a kind of a cake. Okay, cake is a circular and it has height. If I cut this to an angle and take out the wedge, okay, to eat it, okay, so wedge, so that wedge, what is the volume of the wedge? So f r theta r d theta dr, where r would grow from 0 to the end and theta would grow the angle of the wedge. And whatever the equation that we are thinking, f r theta, okay, so that into that we have to calculate and we get. So we'll talk more about, I believe it is big discussion, so we'll talk more about the radial, then cylindric, polar, this is polar coordinate, so polar and then cylindrical and then spherical. Okay, so these coordinates we will talk more. But uh, if I take the Riemann addition, if I take the area and divide into so many rectangles, for each rectangle I have fxy delta x delta y. So delta x delta y into fxy, if I multiply, then I get the volume of that rectangle. In that fashion, if I take radially, then each strip I have to calculate the area, that is f r theta r d theta dr. Then for that strip I get the volume. If I calculate for everyone, I get the total surface into height, complete volume I get. So if I put this one, so if I make the strip, okay, versus, so r, if I take along the r, if I take I strip, along the angle, if I take j strip, like if I have xy plane, then I cut into, sorry, so if I cut it into n strips, so I represent the any particular strip along the x axis. So if I have a surface and x-axis and y-axis, and then x-axis is cut into n part and y-axis is cut into m part, n and m. Okay, n part and m part. So I is the index in n and j is index in the m. Any rectangle is represented as ij. Like that, if I have a kind of a polar coordinate, then rectangle, the radius, I cut radius into n part, and then angular I cut into m part. So any arc is represented as ij. So this will come as f ij r theta r d theta r d theta dr for the ij rectangle. Then I can sum it over everything. Or f ij r theta I can also so f r ij theta ij function over r ij, the r ij r theta j, and then r I j theta I j function over r I j theta I j I jth r I jth theta, and then r d theta dr, or f I j r theta r d theta dr. So this way I calculate the kind of volume of a kind of a wedge in polar coordinate, where the x equal to r theta r cos theta, y equal to r sin theta, and then x square plus y square equal to r square. So this is Cartesian to the polar. So we will proceed on this. I thought that it would be finished today. We will proceed on this. So that we'll see.